interested in stochastic optimization, combinatorial optimization, probabilistic methods, and so on. And one of the broad areas he's been working on has been contention resolution schemes. And today he'll speak about some of their online versions for matching. Thanks.
Great. Okay, so first I'd just like to thank Arvind for inviting me, and also to Renata and Kishan for organizing. So it's my pleasure. I've never been, I think, to Maryland before. Fortunately, I had a friend explain to me that it isn't Maryland, it's Maryland. So I got this ahead of time. Good. So yeah, so I'm going to be talking about a few different papers today, but I'm going to try and focus on sort of the highlights from each of them. So these are joint works with my supervisor at Columbia, so that's Will Ma. And then the first one is actually with Nate as well. And then this last guy is with my co-author Pranav, who's a PhD student of Jan's at Stanford. Good. And so all these papers focus on designing online matching algorithms by this randomized rounding tool called online contention resolution. However, I'm also going to sort of focus on some of the negative results we established, because I think these are quite interesting as well. Good. So before I start talking about what exactly a contention resolution scheme is, I want to try and motivate the most sort of basic reason that people were interested in this topic. And that begins with something called the profit inequality problem. So this is a very fundamental problem where you can imagine I have a single item and I want to sell it to one of n prospective buyers. So each buyer has some sort of valuation function that's drawn from a known distribution D. And what's interesting about the problem is initially the instantiations of these random variables are unknown to me. So instead, I learn them one by one in some sort of adversarial order. And when I learn the value of a random variable, I have to immediately decide whether or not I'd like to take that value. So my objective is I'd like to maximize the expected reward of the item I select. And it's called a profit inequality because I compete against a profit that knows all the realizations of the random variables and thus always takes the expected max. So it's well known that you can get a competitive ratio of 1/2 in this problem, and there's many different ways of doing this. So this is all for when I'm trying to allocate a single item. The problem that we'll sort of keep in mind today is generalization of this to something called profit inequality matching. So the framework's almost the same, except now instead of just having an allocation of a single item, what I'm going to have is a graph. And for every edge of this graph, I'll have a distribution which describes the weight of this edge. Okay. So again, all these edge weights are sampled independently. And again, initially, I don't know the instantiations of these edges. So you can see sort of in the following picture, you can imagine I have this graph on 6 vertices, and on every edge is the distribution, which is provided to me. And then some adversary decides on an order of these edges and presents them to me one by one. So you can imagine I see the edge AB. I see its weight is 2. I decide whether or not I want to take it. And if I do take it, I add it to my matching. Yes? No. So this is an important point. Everything I'm going to talk about in regards to profit inequality it's like called an oblivious adversary. Yeah. So you can imagine for simplicity, the adversary actually commits to some arrival order, and that arrival order is even known to the algorithm. Good. Yeah, so in this case, you can imagine, the algorithm actually knows the exact order the edges are going to arrive, but it's still interesting because you don't know the realizations front. Good, so you can imagine this process continuing step by step. I see the edge BC, I can't take it because I already matched AB. I now learned that the edge BE actually had a very high weight, and at this point, I'm in a bad position because I already matched AB, so I can't take this edge BE. Good. So once I see all the instantiations, the process ends. And in this case, I output the matching of edges AB as well as CF. Good. So similar to the single item profit inequality, my goal is to maximize the expected weight of the matching I output. However, now the benchmark is going to be the expected weight of an optimum matching of G. So you can imagine if, again, I'm the prophet and I get to see the realizations of all of these random variables, I'll always just compute an optimum matching, and what you benchmark against is the average of those. Okay, good. So prophet secretary is very similar, except instead of there being an adversarial arrival order, you can imagine you're competing against nature in the sense that someone draws a random arrival order on the edges, and then they're presented to you in that order. So this is always sort of better for an algorithm, because instead of having to compete against sort of a worst case order, you get the benefit of having random arrivals. And actually today I'll mostly be focusing on algorithms for this secretary. So, okay, so any questions regarding the model? Okay, good. Right, so what's sort of a standard approach for designing sort of this profit matching algorithm? Well, typically what's done in most of the papers is quite actually different than the single item profit inequality, where you're often designing sort of these threshold based algorithms. So instead, what happens here? Yeah.
The story with profit, how did it come?
How did it come?
Yeah.
I see. So, well, okay. So if you have the secretary problem, right?
Yeah.
And secretary, say in the case of a single item, even if the edge weights are adversarial, but they're revealed to you in random order, then you can get 1/e. So
yeah, but that's not the history lesson. So I think the reason that would be good. So the first, actually, the secretary problem, that was the paper of me, Bobby Kleinberg, and David Parks. I think they do secretary because of the auctions.
yeah, I see. Like combinatorial auctions, secretary. Combinatorial auctions.
So that was before that. It is like that. We are talking about the truthful that is the first thing 2004, 2004.
Yeah.
And the people this is like the first paper. Then Bobby Kleinberg had another paper in Soda. Like essentially people know about the second one.
Yeah.
So that's about the secretary. Then we brought the prophet.
Yeah.
Prophet one was the paper of me, Bobby Kleinberg, and Thomas Hartford.
Okay.
That was essentially about the prophet inequality. The first one that we have essentially because of the extension to the CS. And then there was this prophet matching essentially. That was the paper that we had with Said Alai and Raizia. And
This is LA?
Said,
Yeah.
that he was working with me also, but right there we had this one essentially prophet matching the first.
In
prophet
2012,
matching
yeah.
is working.
Yeah. So this is vertex arrival. So this is a fundamental
Yeah, but,
difference.
but that's actually we had the approx paper. It is much more general.
Okay. Yeah.
And the last one, how come the prophet secretary came? Rahid was presenting his thesis essentially, and Arvin was here.
Oh.
And this was essentially the prophets that we were discussing essentially. The prophet, they generally just the order is given to them, sometimes the worst.
Mhm.
And Arvin asked, what about if they are coming in a random order?
Okay.
And that was the whole source of prophet secretary that actually studied. So that, I think
I see. So you should switch. You should talk about. I see. Okay. So you.
How come the prophet secretary came? And we call it a nice name essentially.
Yeah.
But that's like the whole story out there.
I see. Okay. Good. Okay. So.
Yeah.
So I will be talking. So I'm sure I'm mainly going to be talking about contention resolution. I'm going to get to that in a second. And one thing to note is I'm motivating it with profit secretary, but contention resolution is its own problem that has applications in profit secretary, but it has applications in many other stochastic optimization. Yeah. Okay. I'll try to make that distinction a bit clearer. Are you? Yeah.
One question, though, the online version, what other problems?
So say once more.
Like online contention resolution.
Oh, like what other things is it applicable to?
Yeah.
Yeah, so maybe just wait a second, and once I define contention resolution schemes, I'll talk about that. Good. Good. Okay, so where was I? So in terms of designing what a profit matching algorithm is, the typical approach in the matching case is you first come up with some sort of convex relaxation of the offline problem. So you can imagine I have some function Q, and it depends on now no longer just an integral matching of the underlying graph, but a fractional matching. And the way you should think about this fractional matching is the edge value assigned to any edge is like the probability that this offline opt matches that particular edge. So puts it in the optimum solution. Okay, so clearly, this is a relaxation. I'm not exactly specifying what this function Q is, but it's relatively easy to come up with a relaxation of this form that upper bounds the benchmark I just introduced. However, it doesn't actually give you an algorithm because you solve this realization and then you have this integral solution, and we still need to round it back into a integral solution in an online setting. Okay, so this is exactly sort of the role of contention resolution. And the nice thing is, once you solve this sort of offline optimization problem and you're presented this fractional matching, then you can just think of it as an online selection problem. So you can forget about all these complicated edge weights, and it's actually a much nicer and sort of simpler problem. Yes? Good. So I'm kind of ambiguous about how the actual reduction looks here, but this function Q, it actually only depends on the distributions of the edges. So you don't actually need to know the instantiations of their weights. You can compute it. Yeah.
EC 2012, and also there was this paper, I think, is it the expected LP that we do?
Yeah. You can
People change it essentially, but I think that is the expected LP, and that was the main contribution of that one that you can consider, because this XT you are writing in terms of expectation.
Yeah, you can think of basically. Okay, so it's a sum of a function for every edge, and the way the function behaves for a particular edge is it's like the expected value of an edge's weight given the edge is in its like top sort of XC fraction of evaluations. The way you should interpret the little XC is it's saying like, is the edge's weight high enough for me to even consider accepted? I don't want to get too much into how the relaxation goes because it's not essential for the problem, but there's actually multiple ways of doing this.
Yeah, but I think the one that we have done with just XC was just the expected value of that.
I see. I don't. Okay. Well, maybe we can.
Yeah.
I'm thinking about the soda paper. Like,
they just use a new name, etc.
Oh, yeah? I see. Okay. Yeah, I'm thinking of the reduction.
It didn't mention quite clearly what were the new things compared with the board that we have done.
I see. Okay. All right. Okay. Now talked a lot about profit. Let me actually tell you what a contention resolution scheme is, and then for the rest of kind of the talk, we're just going to talk about contention resolution. Okay, so you can imagine I'm in the same sort of setup I had before. So I have this graph on 6 nodes, and unlike before, I'm now going to be presented this fractional matching. So you can think of it as coming from some sort of relaxation or some convex program, but you can also just think of it as an arbitrary fractional match. Okay? And in the offline setting, the way a contention resolution scheme works is the following. So each marginal probability, so each little xc represents the probability that an edge is going to be declared active. So there's only 2 states. Every edge is active or inactive, and the fractional matching describes the marginal probabilities that I need. So you can see in the picture, I flip a coin for every edge. I learn these edge states. Every guy is 0 or 1. And now, if the problem was like super easy, all I would do is I would just output all the active edges. But the reason that contention resolution is interesting, even in the offline setting, is that I'm constrained that I have to output a matching of the active edges. So in this example here, you can imagine, I have these blue edges as being active, and then I can only output, say, AB and CF. Okay. And so what is kind of the goal of a contention resolution scheme? Well, it's to get an edge-by-edge guarantee for the likelihood you're placed in the matching. So more formally, if I fix some alpha, some parameter between 0 and 1, then I want the property that the probability I include any edge in my matching, given the edge is active, is at least that lower bound of alpha. Okay, so this is like a very strong guarantee because it holds on an edge-by-edge basis. So, profit and inequality, technically, you just need to compete against the average value of the matching's edges. Here, it's saying something much stronger. It's saying that if an edge is active, then the likelihood it's matched is at least alpha. Okay, good. So this is all the kind of offline setting. The online setting is very similar, except now I learn the edge states in some sort of adversarial order. So, you know this fractional matching ahead of time. You know that every edge is drawn with these various selection probabilities. but now you have to decide whether to include an active edge step by step. Okay. So it's strictly harder than the offline case, but the goal is the same. You still want to guarantee this uniform selection guarantee. Good. And finally, the random order contention resolution scheme is exactly the same, except now I have this, it's sort of in between offline and online, in that I have the benefit of the edges arriving in random order. Okay, so any questions about the definition? I know it's a bit technical, so please. Okay. All right, so why is this interesting? Okay, well, this is the paper I think of when I think of the reduction, but it sounds like that it maybe came earlier than what I'm saying.
To that, but it
Yeah.
was not completed
Good.
their idea, not even they actually cite that paper at that time, but later this
In the
was
general
cited
version, I see.
officially.
Good. Okay, so the nice thing, and this is what I was sort of alluding to earlier, is that there's a lossless reduction between designing an online contention resolution scheme and getting an algorithm for a profit inequality matching case, right? And this is really nice because then, as I said earlier, we don't have to worry about the complicated distributions on the edge weights anymore. We just reduce it down to an online selection problem where every edge has one of two states. Good. Now, I think someone had a question about this. So while this is maybe the best motivating example for why people care about these schemes, the applications are kind of much more broad. So for instance, the offline setting was originally studied due to as sort of this tool for all constraints and modular optimization. This is an amazing paper, and it's just an offline problem, but they use these contention resolution schemes in a very nice way. And they're the ones who introduced or formalized this idea. There's additional applications, stochastic probing problems, auction design, many other kind of areas they pop up. So what I'm mainly going to focus on is not the applications, but understanding what are sort of the best and worst selectability guarantees that you can attain in both these online arrival orders and in the random order case, as well as for bipartite and general graphs. Good. Yeah, so lower bounds, just remember, are algorithmic, upper bounds are impossibility or negative results.
For general graphs, can you also add the odd cycle streams?
Good. So this is an interesting question that lately been hearing about and thinking about a bit. The bounds, like you can never get a selectability value that's like could potentially, get anywhere close to where like the integrality gap thing becomes an issue. But it does seem like it might be useful to add in additional constraints to the polytope, such as what you're saying, in certain cases. The work I've done, we haven't found an explicit example where like you can clearly get a better algorithm if you make that assumption, but it's definitely a good question to keep in mind. So like, say if I have a general graph and I give you an arbitrary fractional matching for it, there's an integrality gap of like 2/3. So like, even if I'm just like, there were none of these random states, like there's no way of rounding it to approximate an integral matching better than a factor of 2/3. So like what everyone's saying is like, maybe you should impose more constraints on the fractional solution so that it's a more fair kind of setting.
So the outside one? No.
Yeah, these are, you mean like what are they called? Not the butterfly, what's the word? The
Edmonds or?
What are they called again? The flower.
Blossom.
Blossoms. Is this what you mean? Yeah.
We call them those constraints. Blossom constraints.
It's not flower. Okay. All right. Well.
With this.
Yeah, you can push them in, and then for a general, like for bipartite graphs, it doesn't matter. There is no integrality gap, but for general graphs, there is one. So what you can always ask is like, okay, maybe I just want a contention resolution scheme for a fractional matching that satisfies the blossom inequality.
Here is now my problem.
Yeah.
Hypothetically, you can just ignore computational answer.
Yeah, exactly. I mean, yeah, you can, for sure. But often like where you get these fractional solutions from is like an application like profit matching, where because of what the benchmark can do, it actually satisfies these additional constraints. Yeah. Good. Okay, so I know most of these numbers don't mean a lot to everyone, so I'm just going to go through the table. I'm going to point out the highlights. But in basically two of these papers are where these results are coming from. The bold things are like improvements we made, and it's both in the sense that which way does it go? So an arrow inequality towards me is an improved lower bound, and the reverse is an improved upper bound. So remember, this is like just bounds on the selection guarantee that an algorithm can obtain. Good. So I think the ones that are important to kind of keep in mind. So first, for these orange results, these are all positive results in these various combinations. And these actually give the best known competitive ratios for profit secretary and inequality. So it's not just that there is this reduction. This is also, at least currently, the best way to get an algorithm for one of these problems. And the second kind of interesting point is that this 0.074 guy, it's actually the best selection guarantee, even amongst sort of offline contention resolution schemes. So this is sort of surprising. Like the algorithm we presented has to process edges in random order, but there's no algorithm known in the offline case that can beat it, which is kind of strange. Maybe I'll skip the last point, but we do prove a sort of separation. Good. Yeah.
At the because yes, I thought that reduction that shows that for profit inequality, like any approach can be turned into an OCRS.
I see. So this is only against a stronger benchmark called something called the ex ante, which is, yeah, it's a bit, it's not, yeah, it's like a conditional sort of equivalence. Like a profit inequality against a stronger benchmark leads to a contention resolution scheme with the same selectability again. But there's actually examples where, for instance, say the simplest setting where like I have a rank 1 matroid, and I'm just trying to select a single item, like in the first example. There, the best selection you can get is 1 minus 1 over E. But there's profit secretary algorithms that go way past it. They get up to like 0.66 or something. Yeah. Good. Okay, so I'm going to focus. Maybe this is a bit out of order. Let me just check. Good. I might have to skip some of the later stuff, but I'm going to focus on first this negative result. I know usually people start with positive results, but the reason I want to start with the half is because I think the techniques are more interesting, and we think it's the right answer. So I think it makes more sense to talk about what we think the right answer is to random order selectability. Good. So what's nice in this problem is that the actual impossibility instance is very simple. So it's just a complete bipartite graph with uniform edge probabilities. And for anyone who's familiar with random graphs, if I restrict to the active edges, this is precisely like Gn and 1 over n. So it's an extremely sparse Erdos-Renyi random graph. And okay, so in order to prove an upper bound on selectability for this input, we'll actually prove something much stronger and sort of independently interesting. We'll show that no matter which online algorithm you give me, if it processes the edges in random order, then the expected size of its matching is at most n over 2. So this is actually, it's a much stronger statement, and it's sufficient to imply that you can't get a selectability better than a half. Okay. So the first thing to notice is that if I restrict my attention to this input and I accept every active edge greedily, then you can use, say, like Wormhold's differential equation method to analyze this random process, and you can easily prove that greedy gets this n over 2 size matching as n tends to infinity. The problem of why this doesn't immediately imply like this is the right upper bound is that greedy actually isn't the optimal algorithm for maximizing the expected size of this matching. Okay, so why is this not a problem? Well, the suboptimality sort of tends to 0 as n tends to infinity. And okay, so how can you sort of see this? So imagine I'm looking at some edge, and on the greedy algorithm, this is like the last edge that I'm processing, right? Or one of the last edges. If I match this edge and add it, then there's a very small chance that the edges arrive in this very kind of weird order where everything comes on the left and then everything comes on the right. And there's one active edge on either side. And then clearly the algorithm should have taken these two edges instead of the middle one. Okay, so is this actually a problem? Well, no, because the chance that these sort of very rare arrival orders happen is exponentially small as n tends to infinity. Okay, so how do we actually handle these sort of bad rare events? Well, we do it in an implicit way. Okay, so you can imagine now I fix any sort of arbitrary RCRS. So it's not just necessarily greedy, it's any algorithm possible. And now I'll write down the matching that it constructs after the first t edges arrive. Okay. So these t edges, they're presented in random order for me. And what I'm going to do is I'm going to write down the history of these random variables. So I want to know for every edge, what's its identity, which two vertices does it connect? And I also want to know, is it active or not? And then, okay, I can make the very following sort of simple observation is that if I'm looking at this edge at time t+1, then I can add it to my matching if and only if it's active and it doesn't intersect with my previously matched vertices. Okay, so this is sort of two events and they're independent. And what we can prove is that most of the time, so for most of the past sample paths, the history is going to be as we expect. And what I mean by this is that if I'm now looking at my t+1 edge, then its endpoints are going to be distributed roughly uniformly at random. Okay, so why are these two things very useful? Well, what it means is that if I look at the one-step change in the matching, remember this is any algorithm, it's an arbitrary algorithm, then I can upper bound this one-step change, right? So you can see here, the first expression is it active? And the second is, okay, when I drew this t+1 edge, it didn't hit any of my previously matched vertices. Okay, so what's the reason we want to look at this one-step change? Well, let's now imagine that I associate weight n to every single edge. Okay, so then I can look at the weight of the matching I've constructed. If I rewrite the previous expected change that I had, then you can get the following expression where now everything's in terms of the expected one-step change to the weight of the match. Okay, so why is it useful to do this rescaling? Well, now this thing, if I scale everything by n squared, it resembles the following differential inequality. Okay? So if you imagine this one-step expected change is like the derivative of my random variable, and the right-hand side as being what an upper bound and what the derivative must satisfy, then these two things are more or less equivalent. And okay, so in the deterministic setting, if I was just working with differential equations, then a certain domination property occurs, right? So like, if I solve this differential equation and take its optimal solution, then it's going to dominate any solution to this differential inequality. Okay, and what we do is we effectively prove that this also holds in the random set. So if I give you a sequence of random variables that satisfy these one-step expected changes, then the trajectory is still going to be dominated by a scaled version of this differential equation. Good. Okay, and how does this finish the proof? Well, because this domination occurs, I can compare the expected size or the size of my matching with the solution to this differential equation, and that completes the proof because this differential equation has precisely the value I was after. Okay. Good. I'm going to skip probably most of the slide. In the actual conference version, we sort of prove this by hand. In a follow-up, me and my co-author, Patrick Bennett, we proved this sort of general theorem that you can apply, where like if you have a sequence of random variables that satisfy sort of these one-step expected changes, then this phenomenon always occurs. And surprisingly, this sort of type of theorem was missing from the differential equation literature. So for anyone who's familiar with probabilistic combinatorics, like the differential equation method is used all the time. It's like one of the most popular methods. And for some reason, this inequality version wasn't in the literature. And what we do is we more or less show that it continues to hold with inequalities instead of equalities. Yeah, I won't get too much into this because I know it's not maybe that relevant. Okay, cool. I think, so I was going to tell you what the RCRS result looks like. I think I want to, it's just because we're going to finish at 4:30. Right?
34, 40 maybe.
Okay, all right, let me go through this because I want to show you some of the new techniques that I think are more interesting in terms of designing an algorithm. So let me skip over these guys for a second. And good. So I want to talk about this new framework for designing algorithms for RCRSs via something I'm going to call exact selection in continuous time. Okay, so everything else was regarding, like so far has been about negative results. I'm going to jump ahead and show you, these aren't from the first paper, these are from a follow-up work, but I think these are more the right techniques to attaining this half selectability thing. So I want to focus on that instead of the previous results from the paper with Nate. Okay. All right, so let's imagine I'm trying to design an RCRS for this online selection problem. And I'm looking at a particular edge, and now I'm going to imagine it has some timestamp, which is its arrival time on the unit interval. So this is very common sort of way people analyze random order algorithms, is that instead of thinking of a random permutation, you just assign a random time on the unit interval. Okay. So the previous approaches to sort of solving this problem, including the paper I'm now, I guess, sort of skipping, is you come up with some explicit function ahead of time that depends on both the edge as well as the edge's arrival time. So you can think of this as like a function f of e. And these are sort of like an attenuation style algorithm, where like instead of, I can't just greedily accept every edge when it appears and it's active, or I won't get a selection guarantee better than a third. So instead what people do is they sort of, you see an edge arrives and you flip a coin and drop it with a certain probability. And this is, what our previous algorithms look like, as well as pretty much all the algorithms in the literature. In fact, sometimes they're as simple as you just have some functions, continuous function A, and it doesn't even depend on the arrival time. When I see an edge, I learn if it's active, and I flip another coin with some predetermined probability that depends on the edge. Okay. So and other works, for example, for rank 1 matroids, this sort of function f, it actually does depend on the arrival time. Good. So if I look at any sort of, it's a very broad framework, but the selection guarantee you get for such an algorithm can be described by the following integral. And so when an edge arrives, I know I'm going to flip this coin with this prescribed probability specified by f. And then I need to multiply by the probability that the edge is feasible when I actually saw it. So in the matching case, this means its endpoints were unmatched. And like all the work, this is sort of really silly to write out, but all the work is done in sort of lower bounding this probability that when I see an edge, it was feasible to accept. Okay, so the approach that we kind of work on in this follow-up is, instead of defining this function f explicitly, we're going to do it implicitly. Okay, so what do I mean by this? I mean, imagine we've defined an RCRS up until some time y, okay? And we want to extend its definition to any edge that now arrives at time precisely y. Okay, well, since we've already defined the RCRS, we can now compute this previous selection probability, say like by a Monte Carlo simulation, or if you have infinite computing power, we can always compute this feasibility probability. And now let's also decide upon some sort of, I'm going to call it a selection function. And the way you should think about it is, it's going to describe the target rate that I want to select an edge if you tell me it's active and you tell me its arrival time. Okay, so you can imagine, clearly I can't take any selection function, but there's going to be some class of these functions where I can say, like, okay, if an edge arrives at time a half and it's active, I really want to select it with probability c over a half. So it's c of a half. Okay. And then the way we kind of come up with this function f is we normalize by this probability we previously computed. So this isn't going to have a nice explicit form, pretty much like none of the time, but it's certainly a function you can define at this point. And then the nice thing is that if this function f is actually less than 1, then the algorithm is sort of trivially the integral of this function selectable. Okay. So all the work here is determining whether, when I define this function f here and normalize by my previous decisions, I actually get something that's upper bounded by 1. Okay. But the nice thing about this sort of exact selection framework is that we can prove that these guarantees hold in an inductive fashion. Okay. So this sort of approach has been used a lot in the adversarial setting. Like this is pretty much how all the algorithms go. If I'm presented edges in adversarial order, when I see an edge, I compute the probability that it was previously blocked and I normalize by this amount. But that's for like, if I know all the edges and there's a fixed order. Here what's different is now my selection probability depends on an edge's arrival time. And it's maybe a little misleading, but now I'm actually going to do induction on the unit interval. Okay, so what do I mean explicitly by this? Okay, let's fix my parameter y as before. And I'm going to write out the following inductive assumption. So I'm going to assume that this previous RCRS I defined, which is defined strictly before time y, it selects every active edge with the exact probability I want, given that the edge's active status and arrival time. So it's described by this selection function, C. Yeah.
It doesn't depend on the end edge itself.
No, just its arrival time. Yeah. Good. So now my goal is I care about this feasibility term, right? So this feasibility term is what I'm trying to normalize by. So let's just write it out as 1 minus, the probability either endpoint was matched at time y. Sorry, this should be by time y. Good. And then the goal from the previous slide, so if you go back, is if I look at this expression here, I really just want to show this as at most 1. And so equivalently, what I want to show is that this middle equation is lower bounded by my selection function. Okay, so how does this go? Well, we first, this is sort of a technical point, but we can first get rid of this conditioning on the arrival time of y. So what this is saying is that if I take my edge E out of the picture, then that can only decrease the probability that either endpoint U or B is matched.
It's actually independent of that.
No, these aren't independent here. Yeah.
No.
Yeah.
This stuff is independent of sorry.
Yeah. So all I'm trying to do here is like, I want to normalize. This is the expression I care about. I first want to get rid of the condition.
I understand,
Yeah.
but does it depend on the conditioning at all?
Yeah. Like if I commit to an edge's arrival time being at a certain, then it completely changes the previous history of my process, and it can completely mess up this probability. But the nice thing about in this edge arrival setting is when I remove, yeah, exactly, good. So why do I do this? Well, once I get rid of this conditioning, then using, then using my induction hypothesis, I can explicitly write out probability that a previous vertex was matched. So you can imagine I'm looking at U and I'm asking, okay, was it matched before time y? Well, when can that occur? There has to be some vertex W in its neighborhood, which it matches to. And because of my assumption, I just integrate over the arrival time of this previous edge, and I get this explicit upper bound on the likelihood that U is matched. Equality here?
Inequality.
Oh, sorry, yeah, inequality here is.
Yeah.
Good. So yeah, it's not like immediate, but if you think about it a bit more, you can imagine if I'm looking at U and B, and in this side, when I condition on Y, it's like I'm taking the edge E out of the picture, right? So then I'm like running my algorithm up until time Y, but the edge E isn't there.
Yeah.
So what this is just saying is that if I take the edge out of the picture, then that actually hurts the likelihood U or B is matched by time Y. So basically, if I throw in the edge before time Y, it can only help U or B be matched because they're both connected. Good. Excellent. Okay, so what's sort of nice about this equation here is, okay, so we get this easy upper bound, and now we have like a very explicit lower bound on the likelihood that U or B was matched prior to time Y. It's this, you look at either endpoint by itself. I'm completely ignoring any correlation between U and B's matching status, and I still get this lower bound of matching status.
In fact, is it reasonable to assume that U and B be kind of independent, so you can.
Good. So this, I'll talk about this in a second. This, because this actually doesn't match. Okay, well, let me show you. So this is an integral inequality here. It suggests this equation. So I really want my selection function to satisfy this, because if it does, then my algorithm's going to work and be well defined. If you want to maximize the selection guarantee, you should take the equality solution to this. And if you do this, then it has an explicit solution. You can solve the differential equation, and you'll sort of recover this baseline guarantee, actually yours and Nate's original paper, of this like 0.432, right? So it's sort of very different approach, but it gets this, a third is like if you're just greedy, and then you go up to this if you follow your attenuation approach, right? And then this is a different way to recover it. But as to your point regarding the independence, okay, so I don't actually need independence here, but say I have positive correlation between the match statuses of U and V. Okay, so this is a very strong assumption, but if G is like a tree or something, then it definitely holds. And what's interesting here is you can do the exact same sort of computation, but you'll get a different integral inequality. And its solution is completely different, but when you integrate over it, you get the tight half guarantee, right? So somehow, this is sort of, I'm going to talk a bit more, hopefully, let's see on this. Yeah, I'll talk about what we actually do, but these are sort of like warm-up results for this framework. And, we don't beat, it's sort of like in the introduction of the paper, we just sort of show how you can recover some results, and clearly in special cases, you can actually match the negative result. I'm now going to talk about a vertex arrival model where we actually get tight results. Okay, so any questions? I should mention, I'm being a bit misleading. The actual algorithms, we want them to be officially implementable. So we do discretize the unit interval, and then it is proper inductive argument, and you have to do Monte Carlo simulation to get these sort of normalization factors. But the essential ideas are kind of in this sort of, I guess, cartoon proof or whatever you want to call them.
So why do you have to need to compute? I mean, I see, to implement as an algorithm, right?
Yeah. So you're exactly right. Like, but still, this is, maybe we can talk about it after. But still, continuous induction is sort of like not that actually useful. I think there's some technicalities about whether this actually completes an inductive argument. So like, even if you ignore computational issues, you still should do it in a discrete form. But anyway, it's a minor sort of thing. Good. Okay. So maybe talk 15 more minutes. I think that'll be enough time to give overview. Any questions before continuing for that? Okay. So far I've just focused on this sort of edge arrival model and how you can select edges. I now want to talk about sort of the model you originally mentioned. So this vertex arrival guy. But it's different than the vertex arrival model I think you mentioned, because I'm going to think about having general graph arrivals. So like, it's not one-sided. It's like I have vertices arriving on either side of the bipartition, or in a general graph, it's just, vertices arrive one by one. Okay. So it's, yeah. Okay, so again, we're still given this fractional matching with respect to the underlying graph G. And however, now the vertices are going to arrive in random order. And the second difference, and I'll explain precisely what I mean by this in a second, there's going to be some negative correlation between the active status of the edges. Okay, so I'll formalize this in a second, but okay, why do we care about this model? Because the same sort of reductions hold for it. So if I get like an alpha selectable OCRS, then I get an alpha competitive algorithm for profit inequality with random order vertex arrivals. So it's the same sort of lossless reductions. And secondly, this is again to your point. In fact, the model's more complicated. You'll see in a second, but these sort of vertex arrival guarantees are even more useful in some sense. Like if you care about like these query commit matching, price information, or these stochastic matching with few queries, you can actually use these random order contention resolution schemes to get approximation ratios, etc. Cool. Okay, so what is the model? So again, now my vertices are going to be arriving in random order, And so I'm going to have like a timestamp y of b for every vertex. Okay, and so how does it work? Well, let's imagine that my vertex arrives at time y. And now what I do is I'm going to draw some vertex. However, now I'm going to correlate it where the probability this vertex is any neighbor is precisely the marginal probability that I'm given. Okay. I'm now going to refer to the edge as active, provided B selects U and U came before V. Okay, so what does this look like? Okay, firstly, okay, the active edges are sort of batched now, so that every arriving vertex has at most one active edge coming out of it. And this is actually going to be very useful for designing algorithms. Okay, so the goal is the same as before, but you can imagine the following picture. So this first vertex V1 arrives, it has like the smallest timestamp, and there's no one ahead of it, so there's no chance it can generate an active edge. I now go to the second guy, V2, and I make this random draw, this correlated draw, and it happens to select V1. And since V1 is ahead of V2, I refer to this edge as active. Okay, so you can imagine my online algorithm, it now adds this edge to the matching. So the process continues, I get to V3, it draws the first guy, the edge is active, but now because I took this edge 1, 2, I can't take this edge 1, 3. Okay, the process continues, maybe I get to V4, and okay, it makes a random draw, but it either chose V5, so then it actually doesn't have an active edge coming out of it. Okay, and then finally I get to the last vertex, and I again send out this edge. And at this point, I now add it to my matching, and the matching I produce is 1, 2, and 3, 5. Okay, so the way I like to think about this model, if you're familiar with sort of random graphs, is it's like a generalization of the one-out process. So here it's like every vertex selects a random neighbor with, instead of just uniformly at random, it's done such that you're following the marginals represented by the fractional matching. And then we say that an edge is active if the vertices with respect to that selection arrive in the right order. So you can check like the probability that an edge is active is precisely the marginal XUB. And my goal is going to be the same as before. I want to show that if an edge is active, then the chance it's in the matching is at least some universal lower bound alpha. Okay. So yeah, I know the model's a bit more complicated and maybe less natural, but because it's formulated in this kind of weird way, it has very nice applications in the literature. Okay. So in the case where the arrival order is adversarial, it's even for a general graph, it's quite easy to get like a half selection guarantee. It basically just generalizes like the single item case for profit inequalities. Like if I'm just trying to allocate a single item. And then there was a follow-up paper from 2021 that showed that you can strictly do better than a half in this random order selection process. So in other words, random order really does help you for deriving selection guarantees. In this paper with Will, what we do is we show that, okay, if I restrict to bipartite graphs with two-sided random arrivals, then we can get this improvement. So it's like 5, 6, 7. And the nice thing here is that the bound's actually tight. So it's the exact answer for two-sided random order arrivals. I'll mainly just talk about at least some of the positive result. It's going to look like the previous proof. But the nice thing also is that the upper bound, so the negative result, is very similar to the half result I showed you before, but it's actually simpler. So it's again sort of this application of this differential inequality. Good. Okay, so what does the analysis look like? I'll maybe just give you a sort of taste of this. So you can imagine I have some edge E, and okay, when's the first time I can actually even consider adding this edge to my matching? Well, it's going to be when the second vertex arrives. So let's define the arrival time of an edge to be the max of each of its vertices endpoints. This is the first time the edge could possibly be active. Okay, so if I do this, then let's just assume that U comes before V without loss of generality. And now my induction hypothesis is going to look fairly similar in that if I condition on this sort of arrival time of an edge and the edge being active, then it's going to be added to my matching with C of Z or C of Z. And now, similar to before, what I want to do is I want to lower bound the likelihood that this previous vertex U wasn't matched before time Y. And now what I'll be conditioning on is this edge UV arriving at time Y and U coming before, coming first. So the rough idea is that, okay, if I make this assumption, so if we assume we selected edges with the correct probability before time Y, then I want to show that the probability U is E is available isn't too small at time Y. Okay. And the way this goes is the following. So we want to sort of upper bound the chance that U was previously matched before time Y. The first step is similar to before. We have to remove this conditioning on the arrival time of Y. And what's sort of interesting here is, unlike the edge case, this argument is actually quite challenging. But the idea is that because I'm in the setting of the bipartite setting, or I have no odd cycles, if I add in V, then the chance that U is matched can only go up. So what we effectively show is, like, if this probability were to increase, then there had to have been an odd cycle between U and V, but because the graph is bipartite, this can't occur. It's sort of like a coupling style argument. Good. So once I get rid of this extra conditioning that I had, then the arguments, it's very simple.
And if the odd girth is large enough, then you
Yes, I'll talk about that. Yes, and it's actually quite interesting how quickly it converges. I'll mention that in the final slide. But okay, so good. So we want to again apply this sort of induction hypothesis to this match probability. And okay, it's a bit more technical how to write this thing out, and maybe I'll sort of skip through most of the details, but you can again sort of ask, okay, if I look at some previous edge UV, what's the probability that I matched it before time Y? And here I'll condition on both of these vertices arriving before time Y. What you can do is it's a little more complicated because the arrival rate of an edge is described by the max of two random variables. But you get this explicit expression again for the likelihood that U was matched before time Y. And again, just using fractional matching constraints, we can upper bound this again. And what this means is now we get this lower bound on the likelihood that U was matched before time Y. Recalling the initial goal, we then turn this into another sort of integral equation. It's quite different from the first one, but in the same kind of way, what we can do is we can solve it again. We get this different explicit function. And now, because the PDF of my edge's arrival time has changed, if I integrate over the new PDF, then I get this sort of exact 0.576 guarantee. And as I say, it's tight, actually. Yeah, good. So to Aaron's question, so regarding this, so I just showed you this bipartite case. What we actually show in the paper is if you parameterize, you told me the odd girth of the graph, then we get like an approximate result that converges super rapidly, right? So even if the graph's triangle free, so like the odd girth is 3, then you already get almost optimal, like point. Yeah. Yeah, and yeah, good. One thing just to point out, and then I'll just talk about the remaining open problems, is the only part we use this sort of odd girth or assumption is in this step. So it's removing the condition. If you have odd girth, you show like if these probabilities change, then a rare event had to have occurred. And this rare event is unlikely because the odd girth is large and there's not many active edges. I don't have time to talk too much about that, but let me just leave you with a couple of kind of, in my mind, I think, interesting open problems in this space. So of course, the maybe simplest one is, okay, can we get this 0.567 for general graphs? And then second, of course, I just showed you sort of these newer kind of ways to get half for like trees and stuff, but it does sort of make it seem like this is the right answer, especially with our negative result. So somehow it would be really nice to show that, like, in general, this positive correlation can occur, does occur if you do things differently. Anyway, getting this a half is for edge arrivals would be very nice. In the work I didn't really talk about, we do show that if the edges are very small, then via this Gelton-Watson tree reduction, we can get a half. So somehow there's, like, with trees and very small edges, you can get this a half. And it'd be really nice to sort of resolve this. So more or less, the main kind of open problem in this area is, okay, is it really the case that small edges is kind of the hardest setting? Because if you can prove this, then you basically get tight ratios everywhere.
How would you formalize the last question other than second bullet point?
This one?
Yeah, what would be my hardest?
Oh, good. So in every setting, so including the example I showed you, the upper bound of a half, the 0.567, as well as for, I didn't talk about it, but adversarial edge arrivals, all the hard examples in construct, they assume the edge values are like tending to infinity as the graph gets large. So you can imagine, like, they're all upper bounded by some function, epsilon. And as the input grows, like the number of vertices tends to infinity, then the edge values are going to 0. And even in this restricted setting, you can prove hardness results.
Okay.
So, and another way to put it, in certain different contention resolution setups, like not matchings, but other cases, people have proven, like, if you can design a scheme that works for small edges, then you can use it to design a scheme for arbitrary edges. So the open question here is sort of like, can you prove such a reduction?
Oh, reduction like that.
Yeah. Like, in other words, it's sufficient to design a scheme for very small edges instead of arbitrary.
So for example, David Harris once simplified one of our constructions for hypergraph matching by just pointing out that you make multiple copies. So for instance,
Yeah.
if you have a multi-graph here, so.
Good. So that's exactly the seven thing. So matching with multiple edges, it's quite an easy reduction to get it down to, like, if I'm allowed to add in these multi-edges, then I can get a reduction to small edge values. The problem is all these sorts of algorithms have kind of a restriction on there not being short cycles. Like, cycles are somehow what make these problems hard, especially in terms of, like, the independence of matching status explicitly in this asymptotic conversion. So, like, generally, if you put in these multi-edges, it doesn't make the problem easier, even though the edge values are small.